Yes, please. That's marvelous. Well, a very big welcome to Mathari and Dandora girls and Glory Secondary and Kabiro, and of course to Sophia and whoever the Challenge Aid ones are at the moment, and obviously Yestin, who deserves all the Valentines in the world. Anyway, welcome students. It's lovely to see you again. Last time you were fantastically good. If you have a camera, please do put it on because it's nice to see your faces rather than just a thing that says Dandora Girls. Thank you. Today we are continuing with energetics. We have just this lesson and one more, and then we will never do it again. That's the point. So when we have covered today's lesson and next lesson, that's the finish of energetics. We will not do it again until sort of November when we are revising, and we will look very briefly then. So we need to make sure that you can do all the calculations. I'm going to start with a little reminder of what we did last time, and then I'm going to give you two calculations to do. So we're going to start you working straight away. I must say I was very impressed with you last time. It was great. So I'm going to share my screen as soon as I can find my PowerPoint. And I'm just going to go through what it was that we looked at last time. So here it is. This is now Energetics 2. We said that what was in the specification, the syllabus, were these bits and pieces. And last time we did endothermic and exothermic changes. We looked at energy level diagrams, we looked at bond energies, and we looked at Hess's law. Today we're going to start with two calculations, one based on Hess's law, one based on bond energies, and then we will move on to latent heat, which is about physical changes, not chemical reactions. So I will go through just to remind you of where we were last time. So no need to write anything at all at the moment. No need to write anything. So we started with exothermic and endothermic. Exo, exit, the way out, heat is given out. Endothermic, it is taken in. If we look at equations, we will see that in this first one here, 1 mole of methane burns with 2 moles of oxygen to make 1 mole of carbon dioxide and 2 moles of water. And the delta H, the enthalpy change, is negative 890 kilojoules per mole, and therefore it is exothermic because it is lost. The heat is lost from the equation. The chemicals have lost that heat. It has been given out. In nitrogen being oxidized to nitrogen monoxide, nitrogen 2 oxide, it is positive 181, and that means it is endothermic. It will take in heat from its surroundings. That's really important that you remember that delta H is negative, means exothermic, and positive means it's endothermic. We then looked at energy profile diagrams, and I dropped a pen to try and give an example of what I was talking about. In an exothermic change, where we start with are called the reactants, and they go down to the products. In other words, the products are at a lower energy than the reactants. We talked about a stove and cooking, and I said that the reactants have to have some energy added to them to produce the heat in the first place, to start the reaction. And that was called the activation energy, which is here in the purple on the left-hand side. That activation energy might come from a match if we were lighting a stove, or something else, a lighter or whatever. When it comes down the other side, we don't need the lighter or the match anymore because the heat which is being given out will start the new reactants which are there. So the reactants are higher than the products. That is really important. In endothermic, it's the other way up. So the reactants are lower than the products, but we still have energy of activation. The energy of activation now is bigger, and when it goes down the other side, it only goes down a small amount, and therefore the energy change, the enthalpy change, is from the reactants up to the products. That's the heat taken in or absorbed. We then came across Hess's law, which said that if you have different routes to get from one set of chemicals to another one, it doesn't matter which route you take. In other words, the overall enthalpy change depends only on the initial and final states and is independent of the route taken. And we said sometimes we have something like this, where we have reactants on the left-hand side, products on the right-hand side, and sometimes route 1, that is one step, route 2 has 2 steps, but the overall energy change will be the same. And we said that it's sort of helpful if we think about a silly journey, which was from Nairobi to Malindi via Mombasa. And we said, which tickets did you need? If you have arrows which go from Nairobi to Mombasa, but from Malindi to Mombasa, then we have to reverse the Mombasa to Malindi one. We said there was an example which we took, and you guys did it and you got it right, which was fantastic. Here's another example, the things we had to do, and this you should remember or should have written down. You have to find out what can be made into both sides. That's the thing which is going to go underneath this big arrow. Then you have to draw the arrows from them upwards or downwards. Multiply any values, like it has 2 waters on the right hand side, so we need 2 times the energy for that. Change the direction of the arrows if necessary and the signs on the values and add it all up. And we did an example. This is the example we took. Here we found that we have the chemicals for making methane, making carbon dioxide, making water. There's methane on the left, carbon dioxide on the right, water on the right. And in each case, we're starting with carbon and hydrogen, oxygen down at the bottom. So we start with carbon and hydrogen because the oxygen, it balances. We have this arrow, that value, this arrow, that value, this arrow, that value. And then we have to remember that the question mark is from CH4 and oxygen to carbon dioxide and water. And that is the same as going from CH4 and water down to carbon and hydrogen and up again. So this is the one we would have to reverse. So this one would become positive 75. Okay. Then we did bond breaking and bond making, and we came across the phrase bendo-mexo. When we break bonds, it is endothermic. When we make them, it is exothermic. Bendo-mexo. Try and remember it, bendo-mexo. Okay. We then did an example. We looked at an example. The one we looked at was for ethanol to ethene and water. And it was all about counting up the number of bonds which were being broken on this side and then made on that side. So here it is. Here's the whole thing. We draw out the bonds, then we do bendo-mexo, and we said we total up all those which are broken and made. There they are. So there's 1 carbon to carbon single bond over here. That's 347. There's 1 carbon to carbon double bond over here. That's 617. 1, 2, 3, 4, 5 carbon to hydrogens. 1 carbon to oxygen, 1 oxygen to hydrogen, etc. And that means you total them up. This side will be positive, this side will be negative, and then you total them. Okay. So let's have a knowledge check. Let's have a little bit of an experiment, just see if we can do it. So this one here has some equations on the left-hand side and some numbers on the right. And this is a Hess's law, okay? This is one where we write the chemicals across the top. So we're going to start with this there. Okay, so your calculation, I'm going to give you 5 minutes for this. I think it probably won't take you that long, but I'd like you to have a go if you can. So we're from nitrogen and 3 hydrogens to make 2 ammonias, okay? And the thing which is going to go down at the bottom here, if we look at the equations, we have nitrogen, there's nitrogen, making nitrogen monoxide, nitrogen oxide. We have hydrogen making water, and we have ammonia making nitrogen oxide and water. So the thing which is going to be down the bottom here is that. Okay, both sides make the same chemicals, 2 NOs and 3 H2Os, both sides. So just have a moment now, see if you can have a go, help each other. This is not a competition, it's not an examination. The idea is that you see if you can help each other to do it. Okay, so I'm going to stop just for a minute and let you have a go. If you're not sure how to do it, ask your neighbor, ask your teacher, ask your demonstrator, ask your supervisor. They are very clever people. Get them to just hint to you, not to do it for you. Welcome, Silver Spring. I didn't see you there before. Nice to see you. Great to see you. Welcome, Glory. I can now see you, which is great. Very nice to see everybody. Lots of work going on in Dandora Girls, which is great. Matari, you need to ask. If you're not sure, just ask your neighbor. See if they have an idea how to do it. Okay. Osharika, I think you should have the answer by now. Kabiro, working well? Come on, Kabiro. You're going to be the winners today. Yes, you are. Glory Secondary School, they're looking very keen. They're very, very good, Glory. So if you're not quite sure, we have these arrows. We have from ammonia down to nitrogen monoxide and water. We have one from nitrogen to NO and from hydrogen down to H2O. Now the one on the right here is going the wrong way, so it will need to be reversed. But from ammonia down here is this bottom equation here, which is negative 587. If we reverse it, it will be positive 587. Okay, so that's what we've got so far. Got a few more minutes. Some people working very hard. I'm very pleased. Well done. If you come out with an answer which is negative and let's think of the best way of doing this, about as many fingers as 9 or 10 people would have, then you will be right. Okay, if you have a negative answer and about as many fingers as 8, 9, 10, 11 people would have, you will be correct. Has anybody got an answer? Has anybody got an answer they would be willing to share, to show people? It would be great if we could have somebody who would say, yes, I think I can do it. And I think the answer is whatever. Nearly. Okay, I'll give you another minute. Oh, hang on. We have somebody. Ezekiel, who have you got? Hang on. Let me see if I can pin them. Come on, let's pin. Oh, come on. Hang on. Sorry, I need to just change what I'm seeing. Oh. Why can't I make that bigger? Not quite. Remember that the really good construction, but the arrow on the right-hand side needs to be reversed, doesn't it? The arrow on the right-hand side, if you remember, we're going from Nairobi to Mombasa and up to Malindi. Yeah, that was really good go, but just not quite. See if you can find somebody else who can do that, Ezekiel. Really, it's very good. Has anybody else got an answer? Anybody else got an answer? Be really good if somebody else can get an answer. Anybody else got an answer? Oh, well, nearly. That the right hand, Ezekiel, the right hand arrow. Do you see the right hand arrow is going down? It needs to go up. Can you see that? If you show them, Ezekiel, I'm just going to go back for everybody just for a minute. Just going to go back, guys. Let's just look. Look at this one, guys, here. Everybody look at this just a minute. This is sort of similar, but in this one, we had ones going from the chemicals here going up there and up there and up there. So it was going up from the bottom to the left-hand side and to the right-hand side. And what we were trying to get was the question mark, and that is the same as going from the left-hand side down to the bottom and up again, which would mean reversing this one here, okay? Reversing this one here. Now, in our example that we're doing now, here, it's slightly different because we've got it going from the left-hand side down and the right-hand side going down. It's not these arrows that need to reverse, but this one. Okay? So just see if... Has anybody else got an answer yet? Anybody else got an answer? Oh, glory, we have an answer. Can I see it? Ooh! Really close. Really close. Really, really close. Very, very good. Your arithmetic, I think. Come on, Ezekiel, you've got somebody else there. Come on, Ushirika. Ushirika, come on, Ushirika. Kabiro, I know you can do this. Have the courage to say, I think I know the answer. Uh, 452 is better. Oh, hang on, let's have a look. Okay. They've missed out the 3 times for the 3 hydrogens, Ezekiel. There are 3 hydrogens, so we need 3 times the negative 3 at 286. Come on, Dandora, have courage. Bring your picture up. I'm quite sure one of you think you can do it. Come on. Oh, can I see your Sharika? We have one from Ushirika. Up a little bit, please. A little bit flatter onto the screen, please. They say plus 90. They say plus positive 90. They are very good. Ushirika are very good, but, Ushirika, but. Okay, I'm going to stop that because we want to move on. So here we are. What we have to do with this one is we have to go, okay, it is the left-hand arrow from nitrogen downwards. That's here, 181. We have 3 hydrogens going to water. That's 3 times negative 286. 3 times negative 286 will be negative 858. And up the right-hand side, it was downwards 587. So we need to reverse that one. So it is now negative 587, which comes out as negative 90. Okay, so look at the arrows again. Let's go back a bit. There's the original arrows. Remember, across the top is the same as going down and up again. So across the top, which is what we're looking for, it's the same as this arrow plus that arrow plus this one backwards, changed over. So this one has to be negative. So we get positive 181. 3 times negative 286, and up in that direction now minus negative 587, which is plus positive 587, comes out as minus 90. Okay, second knowledge check. Here's another one. Okay, you guys are going to have to do the work today. This is hard, I know. So this one is a bendo-mexo one. This is the other kind of calculation which we had. So this one is nitrogen and hydrogen making ammonia, just like before, but this time we need to see the pictures. Remember, any bonds on the left-hand side will be broken and any on the right will be made. So here we are. Here are the values up at the top. Nitrogen, triple bond nitrogen is 944. Hydrogen, single bond hydrogen, 432. Nitrogen, single bond hydrogen, 389. This is what you need at the bottom in this white square, this white rectangle. We have 1 nitrogen triple bond nitrogen to break. We have 3 hydrogen-hydrogen bonds to make. And then we have 2 times 1, 2, 3, 6 of the NH to make. So total all the left-hand side, that will be positive. We will have to break them. And then everything on the right-hand side, we have to make, which will be negative. So they're all negative. Okay, so have a little bit of a go at that. Just count them up and make sure you do not miss any out. Does anybody think they have an answer yet? Anybody have an answer yet? Anybody with an answer yet? No, not yet. Okay. Just keep going. Remember, on the left-hand side, all of the bonds need to break. Okay, so you have to count up. So we have 1 nitrogen, triple bond nitrogen. That's going to be 944. We also have 3 hydrogen to hydrogen. That means it's 3 times 432. And all of that left-hand side will be positive because it is bendo. We are breaking the bonds, endothermic positive sign. And then we have to add up all the ones on the right-hand side. And they are going to be making new bonds, so they will be negative. They're exothermic, mexo, bendo, mexo. Silver Spring working very well. Kabiro working very well. Glory always seemed to work well. Oshirika, after a small bit of silliness last time, were really, really good workers. Dandora Girls. I seem to remember that Dandora Girls won one of the competitions last time. Mathari next. Mathari Mixed, I think you're going to be great today. Can Ezekiel, get your team out because they had some really good ideas before they nearly got it right. There are the numbers. Let's see somebody get it right. Oh, Gloria have an answer. Gloria have an answer. Gloria coming through immediately. A little bit closer, please. Oh, really nearly. Really, really nearly. Not quite, but nearly. Just try. Just check your arithmetic. Just check your arithmetic. Ezekiel. They're forgetting to multiply, Ezekiel. In the Nightshun, the 944 is right, but it's 3 times. Sorry, I'm just trying to pin it because it's a bit small to see. Oh, could you show me it again, please? Oh, there we are. Oh, it's really close. You've got to multiply by the right number. On the right-hand side, Ezekiel, they're making 6 nitrogen to hydrogen bonds. 6 nitrogen to hydrogen. Okay? Very, very close, but not quite. Okay, so a couple more minutes. Let's get somebody with the right answer. Somebody with the right answer. Come on, Oshirika. Come on. Oshirika are looking a bit sleepy. Maybe they had a hard day today. Maybe school was difficult today. Silver Spring are looking really sharp. Always like Silver Spring. Silver Spring, come on, let's get one of you with the answer because you guys are often really, really powerful. Sorry, Ezekiel, I missed that. Did you want to show me another one? Okay, now it's not 2 times 389. It's 6 times because there are 6 of the bonds. Okay, guys, I'm going to show you on the screen behind me how to do it. Okay, so I'm going to stop sharing. I'm just going to show you on the screen behind me what we have to do. I'll just change my camera. Okay, hopefully you can see this. Let me just see if you can see it mostly. Okay, so here we have the nitrogen is triple bonded. Okay, the nitrogen is triple bonded. We have 3 hydrogens. Then we have 2 ammonias being formed. So the way I do it is this. I go, okay, I know to break this here is 944. So I'm going to break it. Now that has to be positive because I have to put that in. That's bendo. Breaking the bonds is endothermic. It's a positive value. I have to break 1, 2, 3. That will be 432 and 432 and 432. And each one of them is plus. All of that is the bendo. So I have to total all of that. I'm not going to do that for you. You can try that. Over here, I'm making new bonds. And I'm making 1, 2, 3, 4, 5, 6. So I'm going to have 6 times these. But because they're being made, it's negative. Exothermic, it's always negative. So the ones on this side are all going to be positive. The ones on that side are going to be negative. And then you're just going to total the 2 sides, add them together, the positive number and the negative number. Okay, so you just one of those, 1, 2, 3 of these, so 3 times 432. Then over here, 2 nitrogens have, there's 1, 2, 3, 4, 5, 6 bonds, 6 NH bonds. Each one of them is worth 389. So it's 6 389s, and it's negative because we're making them. They give out energy when they make the bonds. Okay? Okay. So have we got an answer anywhere? A little bit further down, please. I can't. No. Oh, positive 90. Okay, we've got an answer of positive 90. From Oshirika. Oh, no, negative 94. Oh, okay. Okay. Who is that, please? Please write your name by that answer. I'd like to see. Teacher Godfrey, you have somebody very clever there. Dandora. Yvonne, was that? Yay, well done, Yvonne. That's really excellent. Well done. Great work. Everybody wants to be Yvonne today. Except all of her people in her class who absolutely hate her now because she got the right answer. Well, she got the answer. Okay, so I'm going to come back to my other camera now. So I hope that helped a little bit. We'll go back to sharing the screen. Here, whoops, here it is. Let's get that out of the way. Here we are. So here's the problem, and it will be answered by going, okay, the bendo is 944 and 3 432s. The mexo, the making the new bonds, is 6 389s, and they're all negative. So we get a total on the breaking of 2240 and on the making of 2334, and therefore we just add those together, and that comes out as negative 94, as Yvonne at Oshirika said. Today, Oshirika produces Yvonne, who is now the teacher, so she can carry on. Okay, here we go. So now what we're going to do is something about latent heat. This is different, and this is a new topic, and we have to understand it and get to grips with it. It is all about solids, liquids, and gases and physical changes. And I'm going to ask you to do something first. I'm going to ask you just to watch a small video by a team who produce videos for all sorts of classes across the world. Probably we'll get an advert first, which is a bit annoying. Oh, yes, an advert. Yes. Okay. Oh, wait. I hope. Can you tell me, can you see the solid, liquid, and gas of a film behind me? Mathari, can you just show me thumbs? Can you see that? Sorry, can you see this blue, yellow, orange? Thank you. Great. Excellent. Okay, solids, liquids, and gases. Okay, now that sounds a little bit complicated, so we're going to watch it again, okay? So we're going back to the beginning, and all I want you to do is to concentrate on what he's saying about what is happening to the temperature. So specific latent heat, or just latent heat, is the amount of energy needed to break the bonds in solid to turn it into a liquid, to overcome the forces of attraction from a liquid into a gas, and so on, or indeed to go in the opposite direction. Now, this is a bit unusual because in chemistry we generally talk about moles, but this is a physical measurement, and it's about the amount of heat needed to change 1 kilogram. Okay. Okay. Oh, I'm sorry if it's a bit, if that was a bit quiet. I'm going to go through all of it anyway. Okay. So, Silver Spring, we have a picture of that being outside. How nice. Some people have escaped from Silver Spring. That's interesting. Okay. I'm sorry it wasn't quite audible. I will make sure that next time I show you it, it is audible. It will be in the recording anyway, and you will be able to see it. Okay. So what we're doing is we're talking about changes of physical state, and this is very important. And you probably know all of them, but you may well not know what is happening during particular changes of state. So here we go. So I'm going to change my, I'm going to share my screen again. Okay. So latent heat, and this may for some of you be worth writing down, that latent heat is only for physical changes. It's only physical changes. Physical changes are solid to liquid, liquid to gas, gas to solid, gas to liquid, etc. Okay, only those. We must not use the term reaction. Okay, when you look at ice turning into water or water turning into water vapor or steam, there is no change in the water molecules. They are changing just from one physical state to another. They are still H2O. Okay? You have to be able to name and describe physical changes. So you have to know all the terms. Now, I'm sure you do, but you do need to know all of the physical changes that you ever come across. You have to be able to describe what happens to the particles, how they are different in solids and liquids and gases. Okay, that's really important in terms of how they're arranged, what energy they are like, and the movement of the particles. Diagrams are often useful. I'm going to show you something else now. I'm going to try to show you something else now, and I hope that it will help you understand what is happening. There's a question here. Do you already know about what happens to temperature during transitions? Just think about that for a minute. Okay, I'm going to stop sharing. I'm going to share something different. I hope you can now see a picture of, come on, up we go. Here. This is meant to be a picture of some particles in a solid. And although it's not easy to see, they are actually always vibrating when they are a solid. Okay, they are always vibrating when they are a solid. Whoops, sorry. Oh, why are you not vibrating? That is annoying. Oh, it is not working for me today. Let's try and start it again. I'll just have to come out of it. Hang on. There is something wrong with my screen. Oh. Okay, it's not going to work. So I'm going to have to draw it on my board. That's okay. Okay. So here are the standard state changes which you should know about. You know the words. It's important that you do know them, but you know a solid melts to make a liquid vaporizes or boils or evaporates. They're all okay to make a gas. A gas turns back to a liquid by condensing. A liquid freezes to make a solid. The slightly unusual one is solid to gas, which is sublimation, and from gas to solid is deposition. You don't need to know about plasma. Plasma is when you get a gas and you strip the electrons from it and it becomes ionized. You don't need to know about plasma and this top one, the top one here on recombination and ionization. But the other changes you should know completely, all those ones there between solid, liquid and gas. The two which people forget are sublimation and deposition. Sublime is going from solid straight to a gas. Sometimes if you've ever watched a video of a music band playing, sometimes they have what looks like smoke on the stage to give a good effect. That is often dry ice. And dry ice it looks like ice, but it's solid carbon dioxide and it does not melt, it goes straight to a gas. That is subliming. But to turn it from the gaseous carbon dioxide into the solid, we have to deposit it to get it to freeze. We have to go down to -78 and we have to deposit it. Okay, so the solid sublimes to make a gas, the gas deposits to become a solid. But all the other ones I'm sure you know. Okay, they will be in this PowerPoint, which I will be sending to your teachers anyway. You have to know about the particles in the solid, and I'm going to talk about those, but I'm going to draw it on the board. I'm not going to use this just at the moment because I'd rather talk to you occasionally rather than show you a slide. So here I go. Okay, when we draw a solid, we should always draw the particles really, really close together. They should be touching. It doesn't matter if they fit into the gaps or whatever, that's how they are. All these guys do is to vibrate. Unless they are down at 0 Kelvin, which is -273 degrees Celsius, they will be moving. Down at absolute 0, they don't move at all, but otherwise they will be moving all the time, okay? In terms of energy, the energy of a solid is relatively low. The movement is quite restricted. It's really just vibration about a point. So if I say the center of this circle here is there, it will just fizz around that. As it starts to heat up, it becomes a liquid. Now, if I put this in a sort of container, what we normally do is we draw the particles away from the sides, which shows that they are self-supporting. As soon as we get to the liquid, of course, they fall to pieces and they fill up the liquid like this. They should still be touching. They should not be too organized. Still should be touching, but they should be disorganized. And the energy is higher than it is in the solid. The movement is now free, but within the liquid. Okay, so they can't get out of the liquid unless they're heated up some more. If we then heat them up some more, they will then become a gas, and they spread out completely. I hope you can see all those pictures. Yes. And at this, the energy is very high, or the highest. The movement is completely free. In this one here, they are locked in position. In this one here, the movement is free and random, but it's random within the liquid. This one is completely free and random again. They can go anywhere at all. So sometimes they'll start here, go off there and come back. It doesn't matter. In theory, a gas will go on and spread out until it is completely spread out in the universe. Now, if we draw a graph of what is happening here, we get an interesting thing here and here. If we take a solid like a piece of ice and we start to heat it up and we attach a thermometer to it, so we get a thermometer and we put it into here and we leave it in here and in here, I'll show you the graph that we get. And we leave it in here and in here, I'll show you the graph that we get. It looks like this. If I am talking about water, then I get a graph where I'm heating up the ice to start with. Let's say the ice comes out as -50 down at the bottom here, and I heat it up and I keep on heating it up. It keeps on warming up, warming up, warming up, and then suddenly it stops warming up. It goes completely horizontal at 0. Now you know that the freezing point or the melting point, depending on which way we're going, the melting point, because we're going up, of ice is 0. But what is interesting here is all the heat that goes into the ice does nothing apart from break the bonds in the ice. Okay, breaking the bonds in the ice. And then it starts to heat up again. So at A, it is just ice. At B, it is ice and water. And then at C, it is water, liquid water. And we keep on heating up and heating up and up and up and up. And then it stops going up again. The temperature stops going up again. And that's at 100. That's the boiling point of water. And so at 100, the temperature stops going up again, even though we're heating it. So when we put heat into a kettle, when the water is boiling, the temperature cannot go up anymore until all the water has boiled away. That's an odd idea, but that's what it is. Okay? So this sort of graph is something we need to draw. We need to be able to draw this. And at A, I have my first picture, which was the solid. At C, I have the liquid. And at E, I have the gas. But at B and D, I have the mixture of the different phases. Okay, now here is a different chemical. This is a chemical called chloroform. Chloroform is CHCl3, trichloromethane. If you look, its numbers on the left-hand side are very different. So it has a melting point of -60. So in other words, it's a solid until -60. And then it boils at +60. So a small, a strange set of numbers. All we need to know is how to tell whether this is solid, liquid or gas. Now, we know about water. We know that water, when we normally come across water, it is a liquid. To find out whether it's a solid, liquid or gas, we take the table like this, the graph like this, and we have to remember that room temperature is around about 25 degrees Celsius. So we can then just draw a line at 25 degrees Celsius and go across, and oh, it's here. See, that makes it a liquid. Okay, so I'm back to my other picture. So in other words, here the temperature can, if I've got just ice, the heat, I can add heat to it if it starts at -50, -40, and it will warm up, warm up, warm up. But as soon as it starts to melt and turn into a liquid, it will stop heating up. And then it will continue to heat up when it's all water. And then the water will start to boil. And at that point, it will stop going up again. So in other words, the temperature in these transitions don't go up. So this is the melting point, and this is the boiling point, and they are fixed numbers. And all the heat that we are putting in just goes into changing the state from solid to liquid, liquid to gas. Now, presumably going in the opposite direction, the opposite thing will happen. So I have to put heat in to go from solid to liquid and from liquid to gas. So if I go from gas to liquid, it must give out heat. And if I go from liquid to solid, it must give out heat. It seems odd. If I take water and I turn it into ice, it gives out heat. That seems odd because we think ice is cold. It's true. But that's why we need a freezer which kicks heat out at the back, because that heat is the heat that it has to take out of the water to turn it back into the solid. So in that direction, it's endothermic. And in this direction, it is exothermic. That's really quite important. Okay, so if you've got the changes, what I want you to do is just to sketch the graph which goes up, cross, up, cross, up. If you already know that, that's absolutely fine. How many of you are already fine with those graphs? Can you just show me? Mathari, Kabiro, Silver Spring, Genesis Joy, Usharika, can you show me if you are totally fine with those graphs? Silver Spring, are you cool with those graphs? Okay, Genesis Joy, are you cool with these graphs? Genesis Joy, gentlemen. Do you understand all those graphs? Not entirely. Some people not. Okay. If you look at the video which will come with this, you can look at it again. Okay, let's move on. We're going to move on now. So latent heat is the heat for the physical changes only. No chemistry, no chemical reactions at all. We mustn't talk about reactions. Okay, on we go. So if you didn't already know it, draw just one of these, and it shows the heat added along the bottom. And then this is solid being heated up, solid melting into liquid, liquid heating up, liquid evaporating into gas, boiling into gas, and then gas heating up. You can heat up a gas. You might not think it, but you can. Every warm day heats up the air around you. That's a gas heating up. Are you, Dandora? Hi, Dandora, do you have a problem?
I just had some issues on the internet, but we're back.
Say again. You had some issues on the internet.
Internet network. Yeah, but
okay.
Back.
Okay. Well, it's nice to see you again. Okay. So the last part to the energy, and I'm going to start it today, but we will do it mainly next week. And next week we will go through all of the calculations, and we will make sure you can do all of them. But this is about measuring and calculating enthalpies. And we can do it practically. And when you, in November or whenever that is, take the KCSE examinations, you will have a paper 3. And in paper 3, they sometimes ask you to do this sort of experiment. It's often a little bit simpler than this because they don't want you to burn yourself with a flame, but they sometimes ask you to measure temperature. This is a very standard way of measuring the heat given out by a little fire at the bottom. If you find it useful, you could draw this. It may be useful to draw it. It is very much something which you may have seen, you may have done as an experiment. If you haven't, next time I could show you the experiment itself. So we have a little spirit burner at the bottom with some alcohol in it, some alkanol. Sorry, it says alcohol. In Kenya, you call it alkanol, like ethanol. And it burns and it heats up some water. Now, we know something about water, and that is that we know how much energy it takes to heat up water. We know how many joules we have to put in to water to heat it up. And here is the sort of question which you get, and it looks pretty horrible. It looks like quite a complicated question. But by the end of next time, you will be able to do this question. I'm going to show you just the first part of how to do this question today. I want you just to read it first. I want you just to read the question first and see if you can understand what is happening. Okay, just read the question. Okay. So I want you just to visualize when you have to answer a question like this. I want you just to visualize, to try to imagine what it would be like doing it. So if you get a glass of water and you think, okay, I'm going to imagine what it is like. They say take a beaker with some water in, and then they put in some sodium hydroxide and they stir it with a thermometer. So you can then imagine that you are doing it. Then it says you have to do various things like draw a graph and so on. And each one of these parts is very, very valuable in marks. So let's have a look at what we do. So here we are. Here's the question. So they're trying to find the enthalpy of solution of sodium hydroxide. And they get a plastic beaker, which weighs 8 grams. They put some distilled water in it. It now weighs 108.15 grams. So there's just over 100 grams of water. Then they add some sodium hydroxide, and it goes up again from 108 to 114. And here are the times and the temperature that it goes up to. So the student is every 30 seconds, they are measuring the temperature. So at 0, it weighed 15. At 30, it weighed 21. At 60, 29, and so on. It says plot a temperature against time graph. Temperature up the side, time along the bottom, evenly spread out so it makes sense. Then it says from your graph, find the maximum temperature attained. Right. Here is the graph. Now I used Excel to produce this, so it's not a very clever graph. But here it is. And what it shows is that as time goes on, the graph, the heat goes up and then it goes down. Now it goes down because the room is cooling the beaker. Okay? And what we have to do is we have to try and see how high the temperature would have gone if all the heat had been coming out at the beginning. Okay, if when we add the sodium hydroxide, if all the temperature had come out straight away, the graph would have gone straight up like this. Would it have gone up to 29? No, it would have gone higher. How do I know how high it goes? Well, what we do is we extrapolate the graph backwards. The idea of that is that we try to not measure, but use the graph to show how much it is being cooled. We do it like this. So when you draw one of these graphs, you go up, and then as soon as it starts going down, you use that cooling to draw an extrapolation, it's called, a line back up to where it started. And then the total temperature rise is not from 15 to 29, but from 15 up to 20, 25, 30, 32 or so. And that's because this allows us to imagine that it wasn't cooling down. So the total rise is not 15 to 29, but this line here, we'll go back, that's the original graph. This line from 29 back down to 26 shows how fast it's cooling. Well, that's the rate at which it's cooling. So we draw the line, and the total temperature rise is from this 0 time, from 15 up to vertically up to the graph where it goes to 32. So it's not 15 to 29, but 15 to 30. It's not 15 to 29, but 15 to 32. So that's the first thing we have to be able to do. That's called extrapolation. If you haven't heard it before, that's what we do. Now, in the question, it then says, so we've plotted our graph. That's normally worth 2 or 3 marks. And then we find the maximum temperature attained. That would be worth 1 or 2 marks. And then the temperature change of the reaction, that's worth 1 mark just for taking 15 away from 32. Then it says calculate the number of moles of sodium hydroxide used in the experiment. Now that is something that a number of you said you would like to do. A number of you said you would like to do some sessions on the uses of moles, the mole concept, and we will do that. We will do mole concept. Okay. Gonna stop sharing now. Okay, so today there's been quite a lot. There's been quite a lot of information. We started reminding you about exothermic, endothermic. We reminded you about bendo-mexo, reminded you about Hess's law and so on. And we're just going to go back to those original 2 calculations so you can remember them again later. Then we've gone on and we've looked at various bits and pieces on the way through, including latent heat. And latent heat is the most important one that we come across. It's almost always there is a question on latent heat. It's not very complicated, but you have to know where it's solid, liquid, gas. You have to be able to read off the temperatures and so on. So I'm now going to go back in my PowerPoint. Hang on. Okay. Okay, I'm going to share my screen. And we're going to look at that calculation again. So this is a knowledge check. Okay, we will do this sometimes. We will look at a particular, whoops, sorry, wrong one. We will look at a particular question which has come up on KCSE examinations. So let's look at this one again. This is Hess's law, and what I want you to do in the last few minutes, we have just a very few minutes, is just to try to remember what we do. If you found it very difficult, look at it again. So this is Hess's law, and we have to look at what we're being asked is this energy or enthalpy change here. So we have to identify from the equations what goes down here to link the 2 sides. We look in here, we've got nitrogen here, there's nitrogen. We've got hydrogen here, there's hydrogen down at the bottom. We've got ammonia here, NH3. Even if you didn't know that it was ammonia, that doesn't matter, it's NH3, there it is. If you look at the total of what is made from the chemicals on the left-hand side. It's N2 makes 2NO, 3H2 makes 3 waters, and that is the same as what the 2NH3 makes. So what is going to go at the bottom here is 2NO and 3H2O. Then we have to be careful that we draw the arrows in the right directions. Okay, the arrows have to go in the right directions. So they're going from nitrogen, from ammonia down to there, from nitrogen down, from hydrogen down. Remember, Nairobi, Mombasa, Malindi. So I want to go from Nairobi to Mombasa, and then at the moment this arrow here is saying I'm going from Malindi to Mombasa. No. I want to go this one backwards. I want to reverse this one. I have to remember, okay, the first one, N2 one, is easy because it is just, that is positive 181. But there are 3 hydrogens. So the 3 hydrogens are 3 times negative 286. So that arrow there is worth negative 858. This arrow down here is worth 587, negative 587, going from ammonia, going from NH3 downwards. But it's going the wrong way. Because it's going the wrong way, I need to reverse that arrow because I want to go Nairobi, Mombasa, Malindi is the same as going Nairobi straight to Malindi. So I have to reverse the one from Mombasa up to Malindi. I want to go up to Malindi, and therefore I have to change the sign and it becomes positive 587. Positive 587. The reason I had 3 times negative 286 is because in the equation it says H2, and here I have 3H2. I have to remember to reverse that one, and therefore I have 181 plus 3 negative 286s plus the reverse of negative 587, and that comes out as minus 90. Okay, I hope you can see that. I hope that it makes a bit more sense now. It's a long time since last week. I'm not surprised you didn't get it because last week we practiced quite a lot. And here is the other type of calculation in which we have to do bendo-mexo. We have to calculate the total number of bonds broken, which will add up to a positive number, and then all those which are negative, which are made. So we have 1 N triple bond N, 3 432s, that's all going to be positive, and then 1, 2, 3 bonds in each of 2 ammonias, that's 6 389s, but they're being made, so it's negative. So it's going to be breaking there, 944, that's that one, the 3 of these, and then 6 negative 389s, and that totals negative 94. Now, what you may notice is that in this calculation, it comes out as negative 90, and in this one, different way of calculating it, it comes out as negative 94. The difference is because the bond enthalpies are average values. You have been very patient. It is the end of the lesson. It's quite complicated what we have done today, really quite complicated. The calculations, the practice calculations may be worth looking at again. When I send your supervisors and teachers the YouTube address for this, if you went just to the end, it will show you those calculations, okay? But everything that we've done today is recorded. I'm now going to stop recording.